Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to demonstrate how to draw shear moment diagrams. So here's the big problem we're looking at here. We've got this beam subjected to this 8 kilonewton load down, this 15 kilonewton per meter distributed load, and this clockwise 20 kilonewton meter couple moment. So typically in a shear moment diagram, the first thing you usually do is find the reactions. You need the reactions for a couple of reasons. One, you would sometimes need them for the free body so that when you actually dig in and do a free body of the beam, you've got known stuff on one side. The other reason you want to have them is because you can then compare your shear moment diagrams to the conditions on the endpoints to make sure your work is good. So in this particular problem, I went ahead already and found these reactions to keep this video a bit on the shorter side. Now, in my original free body, I had AY up, and it came out to be negative 14.3 kilonewtons. I'm going to go ahead and just leave this the way I had it with the force up, and just take note that the actual reaction there is the other direction. All right, so now what we're going to do here is we're going to do a cut in this beam here. And the first cut I'm going to make here is going to be right through there. You need a different cut for every change in load on the beam. So as I look this beam over, we're going to have one set of equations that'll be good to this point right here. Then we're going to have another, we're going to have to cut it again in this region. Then we'll have to cut it again in this region, and then again here. So this problem's got lots and lots of work we're going to have to do here. So starting with our cut in this region, here it is. I'll go ahead and put a shear force in and a bending moment. And there's no horizontal forces anywhere in this problem, so we don't need to put any sort of normal force or anything in this direction. So now we'll start writing force and moment equations. Sum of all forces, y direction equals 0. We do up positive, then we're going to have AY minus our shear equals 0. So our shear force is equal to AY, which numerically is minus 14.3 kilonewtons. Next, we'll write a moment equation. Sum of all moments about A equals 0. I'm going to go ahead and do counterclockwise positive. So summing moments about this point, we're going to have minus our shear force times the distance that I should have labeled here already, x, plus our bending moment, and that's it, equals 0. So our moment function, we're going to get by adding this to the right-hand side. So that's going to be the shear force times x, with the shear being minus 14.3 kilonewtons, and then times x. I think what I'll do is, let's write that minus 14.3x, and that comes out in kilonewton meter, because the minus 14.3 was in kilonewtons, x would be in meters. All right, so I added, so the question I just got is on the plus or minus sign on the shear. So this was added to the right, so it would be positive shear times x. But the shear, the value I have from the force equation, is minus 14.3 kilonewtons. Oh, that's right. Always just be consistent. I'm going to write the equations consistent with the forces in the direction shown, and then I'll just carry this sign along as needed. All right, so we can start our graph now. So, and it's pretty standard sign convention to put your shear moment graphs right below the beam or structure that you're working with. So I'm going to go ahead and draw my axes here. Could have done this earlier to shorten the video up. Okay, so we're going to put my shear function here and my moment function here. So our shear function is constant at minus 14.3, so that might look something like this. This is going to be good to this point right here, where x is equal to 2 meters. And again, that's minus 14.3 kilonewtons. The function for our bending moment is linear with negative slope, goes through the point 0, 0. So this is going to look something like this. This value is going to be, we can calculate by putting 2 meters in for x, and I get negative 28.6 kilonewton meter. I'll just put the units over here, kilonewton meter. All right, so we have our shear and bending moment functions good up to this point. Next step. And fortunately, I have very limited screen room, so all I can do here is just get rid of this stuff. And now we're going to make another cut. Now the other cut needs to be between these. You always want to do a cut between changes in load. So when we go from 2 to 1, somewhere in here, when we get to 1 meter, we add this 8 kilonewton load. So I want to cut somewhere before that. So maybe we'll do this and cut it right there. Whoops. All right, so my cut didn't come out quite like I wanted, but that's good enough. So this couple moment that I had to cut off, keep in mind it's applied right there at 2 meters. And then x is going to be this distance to the end of the cut. That'd be to this point, and we're going to put a shear and another bending moment in the assumed positive directions. So again, it looks a little funny here, but this guy right there, that is the 20 kilonewton meter applied at x equals 2 meters. So I'll go ahead and write a force equation. Sum of all forces, y direction equals 0. So we're going to have AY minus our shear, and that's it looks like, equals 0. So the shear is equal to AY, which again is minus 14.3 kilonewtons. Then we'll write a moment equation. Sum of all moments equals 0, counterclockwise positive. And I'm summing moments about A again, this point right here. So AY doesn't produce any moment about A, but the shear force does. Minus shear times x, that's the distance. Then we're going to have minus 20 kilonewton meter. I'm just going to put NCU for note consistent units on this. Minus because this is a clockwise bending moment, plus the moment we're looking for. I think that's it, equals 0. So our moment function now, let's see, we'd have to add both of these terms. It's going to equal the shear times x plus 20. Keep in mind that the shear is minus 14.3 kilonewtons, so let's put minus 14.3 x plus 20. And again, this will now be in kilonewton meter. All right, so we have functions now that are good from x equals 2 to 3. Our shear has not changed. Looks like it just keeps on trucking. Whoops. Our bending moment is now defined by this linear function. So the first thing we're going to do is put in x equals 2 into this. And that's going to give us minus 28.6 plus 20. So it looks like that's going to be minus 8.6. So that's now here. Minus 8.6 kilonewton meter. I'm going to just double check that. So what I'm doing is I'm putting in x equals 2 to figure out where this function is at x equals 2. And running a 2 here, that's minus 28.6 plus 20, minus 8.6 kilonewton meter. Okay, so I'm going to put that about here. This function is linear. Has a slope of minus 14.3, and it's going to be good until x equals 3. So if we run this, if we put an x equals 3 here, we're going to have minus 14.3 times 3 plus 20. And what I'm going to do here is just take a moment here and get these points and make sure that they end up in the right place. All right, I'm back. So we plotted this function, and again, we just plotted it by putting 2 in and getting this first spot, and then we put 3 in and got minus 23 kilonewton meter out. So here's my x equals 3, y equals minus 23 kilonewtons. So that's going to be, boy, this is getting hard to do here on this spot right there. I'll just do this. There's my minus 23 kilonewton. And again, that's for that level on the graph, which is this point. All right, so we now have our internal shear and bending moment good up to here. Now what we're going to do is we're going to do another cut between 3 and 5. All right, so I'm going to take this guy and we're going to cut it now in this region. Okay, so free body here, we're going to have to add an internal shear and bending moment. Okay, force equations. Sum of all forces y direction equals 0. And I usually just kind of conform and do up positive most of the time. So we're going to have plus AY, and again, that's because of the direction of that force in my free body. Minus 8 kilonewtons for this force vector. Minus the shear force. That's it, equals 0. So our shear now is going to be 8 kilonewtons minus AY. Now keeping in mind that AY is minus 14.3 kilonewtons, so that's going to be 8 kilonewtons plus 14.3 kilonewtons, just 22.3 kilonewtons. Okay, so here's my shear function, and again, this is going to be good from, let's see, x equals 3 to x equals 5. Now we'll start looking at our bending moment. Sum of all moments about A equals 0. All right, so we're summing moments about this point. So the first one I hit here is that minus 20 kilonewton meter. Then we're going to have minus 8 kilonewtons times 3 meters. Then we're going to have, and I should have labeled this earlier, in this case x is this distance. So then we're going to have minus our shear times x for this force vector, and then plus our bending moment for this guy equals 0. Okay, so our bending moment now is going to equal, let's see, we're going to be adding this term. So by the time we add this, keep it in mind the shear is now 22.3. So we're going to have 22.3 times x. I'll put the units at the end of this. Then we're going to have, let's see, this is going to give us plus 24 and plus 40 more. I think that's plus 44, and this will now be in kilonewton meter. I'm going to take a moment here and double check the math. So I left this alone, add the shear times x, shear being 22.3 times x. There's this term, that looks good. Add 24 kilonewton meter, add 20 more kilonewton meter. That's 44 kilonewton meter. Okay, so our shear force is now positive and constant. So that's going to be up here somewhere. So about this location. And again, that's 22.3 kilonewton meter. The units are on there. I'll just put a generic kilonewton meter. Okay, our bending moment, again, is linear. And I think what I'm going to do here is just pause this, and I'm going to graph it by putting in x equals 3, getting a value, and then we'll put in x equals 5, get a value, and plot it. I'm going to pause this for that part. Okay, folks, I'm back, so I'm just going to kind of describe how I got this graph created. So here we had a linear function for our bending moment. This function is good in this region, so it's good from x equals 3 to x equals 5. So our moment at x equals 3 worked out to be 111 kilonewton meter. The moment at x equals 5 ended up being 156 kilonewton meter. So I just put the points on the graph, 3, 111, and 5, 156. Connect the dots. Now my graph is proportionally not correct here now. This is just meant to be a sketch, but It's good enough for now. So we have our function now that's good everywhere in this region. Now we'll start working on this stuff. Now as I get rid of this, it is true that you could do a free body of the right side of this. And you'll actually end up probably being able to solve it quite a bit shorter. I like to just keep trucking left to right, and I like to use the endpoint here to make sure that my equations are good here. I like to use it as a condition at the end to make sure my work is good, as opposed to using that right-hand side to solve it. All right, so there is my last cut. And we'll put a shear and bending moment. Okay. And this guy at 15 got kind of cut, but that was kilonewton per meter. And again, I'm measuring X from here. All right, so this one now has part of a distributed load on it. So this one's going to be a bit more work. Let's go ahead and write our force equation. So sum of all forces y direction equals 0. So we're going to have plus AY minus 8 kilonewtons plus BY, which is 67.3 kilonewtons. All right, now let's deal with this bending moment here. Minus, now, you got to think of this now as a single force vector equal to this area. From here to here is 15. From here to here is X. From here to here is 2, 3, is 5. So the width of this rectangle, and this is an important part of this problem, that green width right there is equal to X minus 5. So the area, we're going to have X minus 5 times 15. And I don't need to worry about the location right now because this is just a shear function where it's located here, or on this force equation is not going to matter. Right? Minus the shear equals 0. So our shear function now, let's see. I guess if I add that to the right and leave everything else alone here, I think what I'll do is here pause this and get this cleaned up and make sure that it's right. Okay, so I'm back, did a little bit of work. Now, all we've done from this line to this line is just simplified stuff, like here's this minus 15x right here. And then the 120 is just coming from adding negative 14.3, don't forget that's minus 14.3, minus 8 plus 67.3, and then this product is plus 75, and here's our shear function. Now before moving on, at this point now, because this cut is good from 5 to 8, we can now check it by putting in x equals 8 into this. And if we put in x equals 8, we get a shear of 0. And when we take a look at the end of our beam here, there is no reaction support here. So the shear does end up having to be 0 right at the end. So what I've did here is, rather than using the right-hand side to figure out shear and moment in this part of the beam, I saved that as a check to make sure that our work was being consistent. So again, this came to be 0 only because there wasn't a reaction force here on the very end. All right, moment equation. And this one's going to be pretty long. Sum of all moments equals 0, counterclockwise positive. We're going to want to be real careful with this one. So summing moments about this point, left to right. So we're going to have the minus 20 kilonewton meter. I'm going to just put NCU here. Note to consistent units and move on because I'm going to probably run out of room. Then we're going to have minus 8 times 3 for this force vector. Then we're going to have, let's see, this guy, plus BY, 67.3, and I just glanced right here for my number, times 5. I'm going to do all the easy stuff first. Minus the shear And for now, I'll just put the shear times x. So that's minus this force times this distance. Now, in my next line, I'm going to have to put this linear function into that, but I'll do that here in a minute. Okay, plus our bending moment, that's this guy. And now let's deal with this distributed load. All right, so now the magnitude of this load we already talked about earlier. This load right here, I'll put it in blue, is equivalent to a single force vector. Magnitude is 15 times x minus 5. And again, the x minus 5 is coming because from here to here is x, from here to here is 5, and then 15 is this distance. And then that's going to be at the center of the rectangle. Now, the width of this rectangle in green, remember, was x minus 5. So these little half distances here and here are both x minus 5 over 2. So, what does that mean as far as our equation is concerned? Summing moments about point A, we're going to have minus, and then here's the magnitude of our force, 15 times x minus 5, minus because this force is producing clockwise moment about A, and then the distance is from here to here, and I'm going to go through it real carefully. 2 plus 1 more is 3, plus 2 more is 5, plus this little half rectangle, which is x minus 5 over 2. So our distance is 5 plus x minus 5 over 2 equals 0. Okay, so there's our moment equation. Again, I'm going to pause this while I work out the algebra and try to get this sorted out. All right, folks, so I'm back here, and I'm just going to be back temporarily. So I went through and did the algebra, just putting in our shear function, minus 15x plus 120. Again, very important to check your endpoints here. So before, I checked our endpoint at x equals 8 here and got a 0, so our shear function was good. Took that function, inserted it here, solved for the bending moment. Be real careful here with all those minus signs and all those distances. We got the following function here for our bending moment. And the first thing to check is what does this look like at the endpoint? So I did that. The bending moment applied at x equals 8, and we got approximately 0 out of that. Now, it's not that they're always 0, but your shear and moment functions have to match up with the conditions at your endpoint. And this thing doesn't have any reaction at our endpoint here. So I was expecting zeros for both shear and the bending moments. So looks like that this function is probably good. It is very unlikely to go through all this work and have it match up your endpoint condition and have it wrong. So we're probably in pretty good shape. So I'm going to pause this again now and then get this thing graphed and then come back. All right, folks, I'm back here probably for the last part of this video. So what we did here, first of all, noticing that this is a quadratic, opens down, we can find the max or min value by looking at the derivative of this. So dm dx would be minus 15x plus 120. Now, hopefully looking here, that was already known to be what we're going to get, because the shear, you should always be able to integrate your moment function and get your shear function. This has a 0 at x equals 8. That means the vertex of our parabola is here. Oh, and the value of this, by the way, is 0. We already checked that when we were talking about whether or not the function was good or not. So again, if you just run an 8 through this function, m of 8, you're going to get 0 out, and that's where the vertex is. Then running x equals 5, because our last equation, again, was good from here to here. So this endpoint would be x equals 5. Out comes minus 69 kilonewton meter. So we know we've got something parabolic that opens down because of the minus sign with the vertex at the point 8, 0. And we know it goes through the point 5, minus 69. That's this point right here. I'll go ahead and put that as a data point. All right. So, and that's it, folks. There's our, oh, I haven't plotted my shear function yet. Let's see. If we put in x equals 5 to this, what's it come to? 5. Okay, thank you. So 545. I don't remember. what this one was. Okay, so 545 is up here somewhere. Negative slope, and we already discussed that if we put x equals 8 into this, the shear ends up being 0. Whoops, make that a little bit better. There we go. All right, so there's our shear and moment functions for this entire structure from left to right. Again, there's shorter ways you can do these. I like to do them very fundamentally by drawing free body diagrams and writing our equations here, but you can do them more mathematically, taking into account knowing that this relationship, that your shear force is equal to dm dx. So once you know shear, you can integrate to get moment, get your moment functions. Again, what I like to do is to derive these from the free bodies and then use the derivative relationship and the endpoints to check my work. It's a little bit longer, but I find it to be a nice fundamental way to work these. So I hope this video helps anybody watching it understand how to draw shear and bending moment diagrams. Have a great day.